Hello, my name is Dave, and we're going to continue talking about hash tables. Um, as you might have guessed from the last video, this structure that we've been slowly building up to is indeed called a hash table, not a medium-sized array. Although we have a little bit more work to go before we can truly celebrate that we've achieved a hash table. Where hashing is this idea that given an object, an element, I can determine for that object the one and only index in the hash table where I might find that object if it appears in my collection. And so, for example, when we looked for Sal, we used a hash function that said, given this object, this person object, ask that person for their ID, their social security number. Given that number, we modded it. We found the remainder when we divided by the length of my array. My array length was 1,000, so we found the remainder when we divided by 1,000. We modded by 1,000, and from that I got the last three digits, 789. And in box 789 is the one and only box where Sal could be. And so, given that object Sal, I can determine what box he belongs in constant time, and therefore, using that ID, I can determine if my hash table contains a person in constant time. I can add a person to my set in constant time by asking the person what box they belong in, and I can remove a person from the set in constant time by asking the person what box they should be removed from if they're there at all, where asking means running them through this hash function. Now, although I was very, very excited to achieve constant time for all these operations, I'm concerned about a couple of drawbacks. One is, and I've written these maybe not in the order I'm going to talk about them. One is I need to determine an integer for each object. So here I relied on the fact that each of my objects had a social security number, had an ID number. And that's great for person objects, but we might worry about, is that going to be true for all objects? And we'll visit that issue soon enough. But the other big issue is, and this was the issue we left off wondering about in the last video, is, isn't it possible that two of my person objects will hash to the same index, like Jim and Sal both do? They both end in the same last three digits, 789, and therefore if I want to add Jim to my set, to my hash table, and I go to box 789, I find Sal is already there, and I don't have a solution to that problem. That's called a collision, when there are two elements that hash to the same index. And, if we think about it, there are many ways we could solve that problem. There's one way that is, I think, far and away the simplest to understand, and that's, what if we don't limit you to just one element in a particular index? What if we let you store lots of elements at a particular index? In other words, what if we have a data structure at each index that stores all those elements that hash to the same index? Maybe we can store Sal and Jim in the same data structure, and we can, and the data structure that we will use, that is traditionally used, is a linked list. Sometimes this idea is called chaining, because it looks like we're drawing a little chain. So we could stick Sal in a linked list, so that means Sal is no longer at that position. Instead, what's at that position is a node, a linked list node, and we can store more than one element at that position, because we can have more than one node in the linked list that corresponds to box 789. So we could put Jim here, Jim, and the full details of Jim's social security number aren't important. What is important is to remember that it ended in 789, and that's what landed him in box 789 here with Sal. Alright, very slight amendment. That means that, technically speaking, we no longer have an array of type person objects. We now have an array of linked list nodes. An array of nodes, 1,000 nodes. And right now, 998 of those boxes are empty, meaning that they store the value null. Let's write a null in here so we can remember. They store a value null, meaning they're empty. There are no linked list nodes here. But this box here contains a linked list with two elements. In other words, refers to the first node in a linked list. And we should probably put Tom in a linked list box to be consistent here. So there's Tom in a one element linked list, where his next is null, meaning he doesn't have a next, he's just one element in a node. And now our structure can accommodate what if we have collisions, what if more than one element hashes to the same index. There's a technical term for these linked lists, and that is they are called buckets. So really, we have our hash table is now an array of buckets, where each bucket is a linked list. And of course, there are many other ways of implementing a hash table, but I think this is the most common and certainly the most easy to understand. Alright, so we've solved the collision problem. We need to focus on generating an integer for each object, but the collision problem actually hasn't gone away. What we've done is we now have a viable way to handle if two objects hash to the same index, like Sal and Jim did. But actually, we lost something very important when we introduced these linked lists, and we're going to have to live with the linked list, so we're going to have to see what is it that we lost, what are the trade-offs of allowing more than one element to hash to the same index. And it turns out what we lost is exactly what we were trying to achieve in the first place, constant time. We haven't completely lost it, but we've sort of lost it. So let's take a look. Let's do our analysis. So now, how long does it take me to figure out if my set contains a given person? Well, now I go to that person, I run it through the hash function, I get their ID, I mod it by the length of my array, I find what index, let's say Sal, belongs at. There's Sal. But now, just because I get to that box doesn't mean I'm done. I now have to walk down a linked list. And we know that the time to walk down a linked list is proportional to the number of elements in that linked list. In other words, it grows linearly in the length of the linked list. So, it seems like we may have introduced linear running times, which would be unfortunate because linear running times are pretty easy to achieve in a data structure, and we were all excited that we had achieved constant running times. Well, let's make a list of the actual running times going on here. So, the contains operation, it's true, it now has a worst case possibility of being linear, and we're going to keep this analysis really simple. We might do a more rigorous analysis in the future. To determine if my hash table contains a given value, well, the worst case is I get to a particular bucket, and it turns out, well, what is the worst case? The worst case is that every single element in my hash table ends in the same 3 digits in this case, or in general, hashes to the same bucket. Every single element is in the same bucket. That would be the absolute worst case scenario. And when that occurs, the hash table will be doing nothing for me, and I will basically have a linked list, and the time to determine if the linked list contains a value will definitely be linear in the number of elements. If I have n elements, it will be order n. But it could be better than that. We have a best case time. And the best case time is, well, best case time, I suppose, is you jump to buckets. Let's say we're looking for someone whose last 3 digits are 999. We go to bucket 999, and it's completely empty. So, in constant time, we can determine that our set does not contain that element. Also, it could turn out we get to that bucket, but it's the very first element in that bucket. Or maybe we get to that bucket, and it only has one element. And I think in any of those cases, we could argue that the running time is constant, that it doesn't depend on the number of elements. So, the big question is, I don't get too worried about worst case or best case. The one that I care about is, what is the expected time? What's the expected case? What's the typical case? What is the average case? Now, technically, the average is, well, let's see, it depends on a great many things. It depends on how good is your hashing function. Our hashing function goes by the last 3 digits of a social security number, and it turns out most people have pretty random last 3 digits of their social security number. This is a good choice of a hash function. And we'll look at some other bad hash functions coming up soon. But this is a pretty good one. We might expect that the elements get spread out pretty evenly. And if I have a long enough array and few enough elements, and I'm usually going to make sure that my array is pretty big relative to the number of elements, if that's true, then I might be reasonable thinking that this is constant time that I expect. So let's put an asterisk there and explain where that constant time is coming from. That constant time is coming from the fact that I assume I have a good hash function, meaning that elements are distributed fairly evenly across the many buckets, and I am going to assume that I have a sufficient number of buckets, where sufficient means I have enough buckets that most buckets are going to be relatively empty. Therefore, most of the time I'm going to have an empty bucket, a one-element bucket, a two-element bucket, and I can say that my expected time is constant. So that's contains. We could look at the others, and we will. But it turns out the running time for add and the running time for remove ends up being exactly the same as contains, which is the worst case is everything's in the same bucket. Actually, the worst case for add is a little tricky because if my set does not allow any duplicates, then when I go to that bucket, I still need to walk through the entire linked list just to determine that my new element is not already there so that I can add them. So the worst case is I walk through a really long linked list and I find that they're not there, so now I can add that element. So that's going to be linear time. But as before, I'm going to expect that my buckets are pretty small, and therefore I'm going to expect constant running times, and the same thing with remove. My worst case is I have to walk down a really long linked list to find and remove an element, but I expect that my buckets are really small, in which case I hope that on average I'm not going to have to spend very much time, that the time is not going to depend on the number of elements, and I can remove in constant time. I will see you in the next video.